All right, so let's go ahead and continue on with our class. I'm going to make a few announcements towards the end of class, just waiting for last minute people to come on in before I make any sort of important announcements. So we'll start off with the trajectory of the class. We'll start off with content. And last time we were discussing this idea of vectors. We were talking about vectors. Why do we do that? We do that because they describe for us very well different physical quantities. So we talk about vectors, and we talk about vectors to talk about physical quantities. And one area of physics that we are really interested in studying are physical quantities related to motion. And that's where we're starting off this class. Physical quantities related to motion. So we asked the question, what quantities are related to motion? And we start to think, well, how might we describe motion? Well, if we're describing motion, we're describing how an object shifts from one location to another. Well, now, how does it go from point A to point B? Well, to understand how it goes from point A to point B, we need a way to describe where point A and where point B is. So we need to first describe the position of whatever it is we're looking at the motion. So we say, okay, well, we want to know position of whatever it is that we are looking at. And how might we do this? Well, we look at a whiteboard and we say, I'm going to mark an X on here. I'm going to say this is at some position. That X is on some position. Where is it? It's right there. But that's not super helpful to say, the position is right there on the whiteboard. That's not the most helpful thing. Because, well, how can we really analyze the position if we just have some qualitative understanding that it's over there? So instead what we need to do is start to create a coordinate system by which we can understand our position. So we want to understand our position, the location of an object, we define a coordinate system. And if we're talking strictly one-dimensional meaning, left and right perhaps, or maybe up and down. If we're talking one-dimensional, our coordinate system is just a number line. So we create a number line. Say, here's our number line. And on our number line, we can now mark the position of whatever it is we're looking at. Maybe we say position is located right there. And now we have a position on a number line. We have a position on a coordinate system. Now this is again a one-dimensional coordinate system. We'll look at two dimensions, see how that changes. But we have a position on a one-dimensional coordinate system. Wonderful. But still no numbers, right? Still no numbers. In order to introduce numbers, in order to quantitatively analyze our position, we need to define where we call our origin. Our origin is the place where our position has a value of 0. So you say, where is the origin? We pick a place. Now, we can pick maybe far left to be our origin. We can pick the middle to be our origin. We can pick our far right to be origin. The choice of origin is arbitrary. Because when you start to get to motion occurring, you're looking at changes in position, your origin ends up not having an effect on what that overall change in position looks like. We'll see that as we go throughout the class. So we pick a place. Where do we want the origin to be? We'll pick A, B, or C. Where do we want the origin to be? I want you to put up 1 finger if you want it at A, 2 fingers if you want it at B, and 3 fingers if you want it at C. Go ahead and do that. Raise it up high. I'm going to take what I seem to think is the average, and it looks like the average is going to be, it looks like 2. Looks like 2 wins out, so we'll put the origin right at B. We say, here is our origin, 0. So we defined our origin. Wonderful. This gets us one step closer to understanding position, because now we can say whether our position is to the left or to the right of the origin. And when we look at this, is our position to the left or to the right? It's to the left. If we look at our origin right center, meaning our position is to the left. So we have an indication of direction. Left or right gives you direction. Left is different than right, so it gives you two unique directions. So we have this understanding now that our position is to the left. But how far to the left is a new question. Remember, when we deal with these vector quantities, we are asking the question not only where is it, but in what direction, right? Vectors always have magnitude and direction. We figured out the direction. Direction is to the left of the origin. Now we need a magnitude. So we start to fill out the rest of our coordinate system. Maybe each of these ticks represents 1/10 of a meter away from the origin. So we have 0.1 meters, 0.2. And why am I putting the negative sign on there? I'm putting the negative sign on there because traditionally when we look at a number line, to the left is the negative values, to the right is the positive values, right? This is a convention that we still hold on to even when we talk about physics. We hold on to these mathematical conventions, bless you. We hold on to these mathematical conventions that says to the left is negative and to the right is positive. So we say positive is to the right, negative is to the left. Again, holding on to those same mathematical conventions. Does that sound all right? So we have this idea, okay, our position. Where is our position? Our position is 1/10 of a meter to the left of the origin. That's how we would phrase it. We would say our object is 1/10 of a meter to the left of our origin. That puts together three things. Puts together direction to the left, magnitude, 1/10 of a meter, and it gives us a reference point from the origin. Those three things give an exact location of where this object is, where the position is located. It leaves no ambiguity because we have this exact location, we have this exact numerical way to represent this. Now, writing out 1/10 of a meter to the left of the origin, that's a mouthful, right? That's a mouthful, and it tends to not be particularly useful when we start discussing mathematics, right? How do you do algebra with a sentence? Well, you can't really. So instead, we come up with a more mathematical description. And our mathematical description uses this left and right positive and negative notation. Because now instead of writing out 1/10 of a meter to the left, instead of writing out 1/10 of a meter to the left, well, what can we do? We can say to the left is equivalent, bless you, is equivalent to saying negative. So we can say instead negative 0.1 meters. Because the only location that is negative 0.1 meters is 1/10 of a meter to the left. That leaves no ambiguity, so it tells you your initial position is 0.1 meters. That sound reasonable? Okay. So you say initial position. How do we represent initial position? Well, I am going to use the variable letter x to represent position on a horizontal axis. We'll do something different with vertical. A horizontal axis, our horizontal position is represented by x. So I might say the object has a positional location 0.1 meters to the left, negative 0.1 meters. So that's how we would write that. Does that sound relatively all right? Any thoughts about that? We're good? All right. If you guys have any questions, be sure to stop me. So we have our location. Right? We have our location. We have a way to describe our location. Let me throw out another one. What is the location of the blue marker? Right there. What will we say that location is? Positive 0.2 meters. Or we could say 0.2 meters to the right. Positive 0.2 meters. So we might say the blue position, 0.2 meters in the positive direction. Now we don't have to put the positive sign in there. We don't have to because the positive is assumed. We explicitly say when something is negative, but we can just include a positive value. But this again gives you magnitude and direction, the two parts of a vector, magnitude and direction for our position. To the right of our location, vector position of our object, whatever it is that we're putting down. And with any vector position, we specify left, right, or up and down with an I hat or a j hat, those unit vectors. So what does this read out? What does this read out as? This reads out as our vector position Equal sign means it's described by, is quantified by. That's what the equal sign means. It means this is that value. Is equal to 0.2 meters, the magnitude. The magnitude, how big is this position? In other words, how far from the origin is it? And then I hat gives you the specific direction. A positive I hat means to the right, and negative I hat means to the left. Seem reasonable? Yes? Okay. We look at a different coordinate system. Maybe instead of looking left and right, we look up and down. We say, here's a new coordinate system. We're looking at something that is located vertically. Maybe we're looking at something whose altitude is changing, right? The up and down direction, the altitude. Something that is changing in altitude, well, typically we use to represent up and down y for our values. Positional y position. And just like any other coordinate system, we need to define an origin. Now we have choices to make. We can say A, B, or C is our origin, right? We can choose which origin we want to use. Again, the choice of origin is always arbitrary. So, quick show of hands. 1 if you want to use A, 2 if you want to use B, 3 if you want to use C. What origin do we want to pick? Raise your hand up high for that value. See a good amount of 3s, some 2s. The occasional 1. So we'll use 3. It looks like that was the majority. We say C is our origin. C is our origin. That is the place where we have a 0 for our positional location. If we have an object that is located at that point, we would say the position is 0. It is 0 meters away from the origin. Our location is 0. But if our object is anywhere else, we start to have a different, a numerical value we can assign to those positional coordinates. So we fill out the rest of our coordinate system. Perhaps this is 2 meters, 3 meters, 4 meters. And traditionally speaking, this will not always be the case. Sometimes we use positive going downwards, but traditionally positive will be up for our values of position. Positive is up, above our origin, whereas negative values would be below. Now, when is a time you might make a differing choice there? When might you choose positive to be downwards? Well, if you guys have ever gone diving, I've never been diving before because I'm terrified of the open ocean, but if you guys have ever been diving before, as you go downwards, you're considered to have a positive position. Downwards is positive. Depth is positive. So sometimes when you talk about things going underwater, you start to use positive as your value of position. And we'll do that later on in the semester when we talk about fluids. But for the most part in this class, we can take positive to be upwards. Oops, I mismatched my units here. It should be 2, 4, and 6. So we look at this and we say, well, what is our position? What is our position going to be? Well, take a marker, say that is our location. That is our location of some object X. How would we represent its position? We would say that that has a position of y equals positive 3 meters, right? That is our position, our vertical position of our object. We can look at this and say, well, positive 3 meters, this is something that has a magnitude 3 meters, positive meaning a direction, and we can be explicit about the fact that this is vertical motion. We can be explicit about the fact that this is vertical in its quantity by saying it's 3 meters in the j hat direction. Remember, j hat means vertical, up and down. I hat means horizontal, left and right. J hat means vertical, up and down. So if you see something that has a positional vector, 2 meters j hat, 2 meters j hat means that the location will be right here at this blue mark. That would be the location. That sound good? So I ask you if we had a third location. Let's break out this green marker. let's say we look at a third location right there, how would you represent your position vector? How would you represent your position vector? I want you to talk to your neighbor, tell your neighbor how you would represent this position vector. Turn to the side, turn behind you, in front of you, and ask your neighbor, how would you represent this vertical position for this green position? Hearing few answers. Does anybody want to venture a guess? Raise your hand if you want to share with the classroom what your answer to what the vertical position is of this green circle. Who wants to share? Right up front.
5 meters J hat.
5 meters J hat, absolutely. 5 meters J hat. Now, I know what you're saying. You're saying, Professor Martinez, why are we doing all of this? This is really basic. This is really easy. I came to physics to be challenged, right? So, of course you did. Of course you want to be challenged. So we then ask the question, what occurs when we start looking at motion that isn't strictly up and down or strictly left and right? We now look at something that can exist on a plane, 2 dimensions, right? We ask, what does our position look like when we have 2 dimensions? Well, to have 2 dimensions, we start to open up this idea of a Cartesian coordinate system. We've all used Cartesian coordinate systems. We were using them last time we were here, where we take a Cartesian coordinate system that allows us to represent positions x and y at the same time. Traditionally, with our Cartesian coordinate systems, we say our origin is the place where the 2 axes cross, right? This is our origin. Now, we can make other choices if we really wanted to, but this is a convenient one to make. We look at this and we say, well, we can go to the left and right. We can go up and down. So I'm going to mark off a few ticks here to represent different units of length. So we say, here's our origin, where our axes cross. To the right, anywhere on the right side of our origin, anywhere to the right would have a positive x value. So we'll say this is 1 meter, 3 meter, 5 meters going to the right. And to the left, we would have -1 meter, -3 meters, -5 meters. And I'm skipping every other one just for the sake of keeping things a little bit clean. But we mark out our x-axis, our horizontal axis, to be positive to the right and negative to the left, just like we were doing before. We then look and we say, well, vertical, we can say 1 meter, 3 meter, 5 meters up. And again, positive for upwards. If we wanted to go down, we absolutely could. We can go downwards and say -1 meter, -3 meters, so on and so forth. But we build out this plane that allows us to quantify any position that exists on this plane. And we say, well, perhaps we look at the position right there where that green mark is. Well, we say that the horizontal position is +3 meters, right? And our vertical position, well, our vertical position is 0. So we would say that the position here is 3 meters to the right, 0 meters up. What is the position? How do we represent that? Well, we represent that position as being so how would we represent that position? We represent that position as being a 3 meter I hat plus 0 meter j hat. We don't have to include that. We can just say anything times 0 is 0. So we could just write 3 meters I hat if we want to. I'm just writing it this way for completeness. Then we say, I want a variable letter to represent this. I want a way to mathematically write this out using a variable. We use x for horizontal. We use y for vertical. What are we going to use here? And different sources will have different answers to that. Sometimes sources use x to represent any position. Oftentimes, though, a nicer notation is to use the letter S to represent a position. S, or sometimes R is used, but we'll use S here. We'll say S is your arbitrary positional location. S is position. This is where we are looking at. So S is 3 meters, 0 meters. That leaves this to be the only location that can be represented on this, yeah? Let's try another one. Let's look at a different location. Let's take this marker and say we are looking at that location right there, the red location. What is that red location? That red location will have a position given by what? Well, we are 2 meters to the right and 4 meters up, right? So how would we write that? We'd write that 2 meters to the right and 4 meters up. We have our positional location. And this is a vector, right? This is a vector. It tells you specifically what direction it is, left, right, up, and down. Any questions about this so far? Not too bad, right? All right, here's what we're going to do. Give you a third location. I haven't used blue yet. Here's a third location. On your paper, I want you to mark out on a coordinate system where this location will be. Mark out the location of this third point. Mark out the position of this third point. All right, now what I want you to do is show your neighbor where you marked on your paper. Show your neighbor where your position is. See if your neighbor and you agree. So you have the same position for that blue point. All right. So the position you should have marked was 2 meters to the left. Negative 2 meters means to the left. And then 3 meters up, the position you should mark, that location right there. Not too bad, yeah? Okay. So now we have an understanding. We have this understanding. How do we describe the location of an object? Well, you describe a location quantitatively with this position vector. This position vector that tells you where you are as it relates to some chosen origin. Now, the chosen origin is arbitrary, right? You could choose a different origin if you want to, but in the most of the time, the choice you make will be obvious. So we have this idea. How do you describe the location with this position vector? But we're here to describe motion, right? We're here to describe motion. When we talk about motion, we're saying, how does an object go from point A to point B? Yes, we have a great way to describe where point A is, where point B is. Let's say that this location that we just marked off in blue is position A, location A, perhaps where an object starts. And let's say it goes from point A and it moves to point B, perhaps right there. We'll call that position B, S subscript B. So the question is, how does it go from point A to point B? How does it go from one position to another? Well, the easiest case would be to say that it undergoes some straight path from A to B. Our object starts at A, ends at B. What is the change? Well, the change goes from A to B. We want a way to describe this. How do we describe this? Well, the best way we can do that is with a second motional quantity, the motional quantity of displacement. The motional quantity of displacement describes how an object goes from one point to another. Well, it describes the actual change from one point to another. So our displacement, we want a way to describe going from point A to point B. Now we can look at this green arrow item, right? And we can say, well, to go from point A to point B, how far to the right do you need to move? 5 meters. So the displacement should be 5 meters to the right. How far vertically do we move? What's our change vertically? 2 meters. In which direction? Downwards, negative, j hat, absolutely. So what does that mean? That means our displacement here should be 5 meters to the right and 2 meters downwards. This is a vector quantity. I'll put an arrow over top. So we look at this. We say we move 5 meters to the right, 2 meters down. This should describe my displacement. Does that sound good? But there's got to be a better way to do this. There's got to be a better mathematical way to write this out. So how do we do that? Well, first we need to have a good description of our positions, right? And we had position A written out. We said position A is represented as negative 2 meters I hat plus 3 meters j hat. And then we ask ourselves, well, what is position B? Position B, we look at it and we say, well, it's 3 meters to the right, 1 meter up. Position B is 3 meters I hat and 1 meter j hat, 1 meter up. And do we feel good about that? So then what is the mathematical operation we can do with our positions to get this 5 meter right, 2 meter down displacement? Well, it seems to be the case that if we take position B and subtract off position A, well, it seems like that might give us the displacement value that we see present. How can we prove that? Well, we prove that by saying that this is going to be position B is 3 meters I hat plus 1 meter j hat. And you subtract off your position A, which is negative 2 meter I hat plus 3 meter j hat. What are we doing here? Algebraically, we're just plugging in our position B and our position A. Now, pause and we look at that, we make sure, okay, I can see the algebra there. I can see how we're just swapping out position B and position A. We look at this and we say, okay, well, how do we mathematically solve this? First thing we might want to do, distribute the negative into the parenthesis. We might want to get rid of the parenthesis first. Remember, order of operations is important here. So we get rid of the parentheses. And if we get rid of the parentheses, what we have is 3 meters I hat plus 1 meter j hat. Negative negative 2 gives you a positive 2 meters I hat and a negative positive 3 meters, a negative 3 meters j hats. So we distributed in that negative. And at this point, it's just algebra. All we're doing is algebra. So we take this and we say, well, I have a couple of like terms here. I have 2 terms that have that I hat piece. Since I have 2 terms that have that I hat piece, we can combine them. 3 meters and 2 meters are the coefficients that multiply the I hats. And then we have 2 terms that have a j hat in it. So we say that's plus 1 meter minus 3 meters j hat. We combine our like terms. Whenever you're dealing with vectors, you're going to combine the vertical pieces, the j hat pieces. You're going to combine the I hat pieces, the horizontal pieces. And this gives you 3 plus 2. Well, 3 plus 2 is 5 meters I hat. And then we have 1 minus 3. 1 minus 3 is? -2 meters j hat. Exactly what we said the displacement should be. So our displacement seems to just be the difference between our positions, specifically taking our final position and subtracting off our initial position. So our displacement can be described as a change in position. Delta we use in physics to represent changes. So we say it's delta S, our change in position, is given by our final position minus our initial position. And this is the definition for our displacement. This is the definition for our vector displacement. And it does end up being a vector, right? Because we have these I hat and these j hat components, these components that tell us this is the direction our displacement is in. It's to the right and it's down. So I marked off two positions on the board, an initial position and a final position. We're going to imagine an object starts at some initial position given by that location and ending at some final location given by that second S subscript F. Those are our initial and our final location. My question is, if this is your initial and final location, what is our displacement? What is our displacement? Starting from initial to final. I want you to first work this out independently. You're going to first think, what is it? So work it out independently. Find that displacement value. All right, now what I want you to do is take that displacement, which you surely just found, and show it to your neighbor. Make sure you and your neighbor have agreeing displacements. Make sure that you guys have the same displacement.
Yeah, I know.
That's all right. If I can't see it, I'll just tell you. All right, we're going to do a little bit more time on this. Okay, I do apologize for those who want more time. Majority rules. We're going to look at this and we're going to move a little bit forward. So the question is, what is our displacement? Well, our displacement is going to be what? It's our change in position. Our change in position, our final position. Our change in position, which is our final position minus our initial position. So the first thing we do is we figure out what is our initial position, what is our final position. Our final position is going to be -2 meters plus 2 meters I hat, j hat. So that's our initial position. -2 meters I hat plus 2 meters j hat. Did I get that right? For our final position. Then our initial position, well, our initial position is going to be 3 meters I hat plus 5 meters j hat. So we take the difference of our position vectors. Remember, this is just algebra. Now we multiply in the negative, and then we combine like terms. When we do this, we should end up with 5 meters, -5 meters I hat for being our horizontal component. How many of us got -5 meters I hat? Wonderful. And let's see, does that make sense? Well, if we look at this green arrow, our green arrow does in fact go over 1, 2, 3, 4, 5 meters. So it does seem to match up. Wonderful. Then we look at the vertical piece. Well, we have 2 meters minus 5 meters. 2 minus 5 is -3 meters j hat. And does this make sense? Yeah, absolutely it does. It looks like we go down 1, 2, 3 meters to get from our initial to our final. So this gives us our displacement. See, good? Thoughts, comments, concerns? All right, so we have this position, we have this displacement, we have a way to quantify both of these. In other words, we have a way to answer the questions, where is an object, where was an object, and what was the change in that object's location. We have a way to start describing our motion, but this change can look a few different ways. Maybe this change was very slow, maybe this change was very quick. Maybe this change was at sort of an average pace. So there's a question now, what did this change actually look like? And when we ask the question, what does this change look like, we might be asking the question, how quickly did this change occur? How quickly this change occurred, well, that's the physical quantity of velocity. So we ask, how quickly did this change occur? Now, there are a few different ways we can do this. We'll start with the easiest way to describe velocity. We can first start off with one dimension. Let's go back to one dimension, and then we can expand off to 2 dimensions. And if we wanted to do 3 dimensions, it's not that hard of an extrapolation. But we'll start off with one dimension. We'll say an object moves left and right. Here's our number line. Our number line describes our coordinate system in one dimension, and we orient it horizontally if we're dealing with horizontal motion. We need a place to put our origin. We need to choose a place for our origin. Hold up 1 finger for A, 2 finger for B, 3 finger for C. Where are we putting our origin? Hold it up high. Looks like majority is 2. So we'll put our origin right here at the central location. That is our orbit. Now we have to look left and right to see, what is our actual values, what is our unit of measurement here. So we look to the right and we say maybe this is 2 meters, 4 meters, 6 meters, negative 2 meters, negative 4 meters, negative 6 meters, negative 8 meters. So we have our coordinate system well defined, and with a well-defined coordinate system, we can now start to create motion that is definable. And for our motion, we'll say that we start at the red line. This is our start at the red X. Sorry, not line, an X. And we'll say that we move until we get to some final location, represented by the green. Then we ask ourselves, well, what is going to be our displacement here? Well, our displacement is going to be 10 meters to the right, yes? So our displacement here is 10 meters in the i-hat direction. We say, here's our displacement. Our displacement is 10 meters in the i-hat direction. Our displacement, delta S, is 10 meters in the i-hat direction. And it's positive, and that positive indicates to us what? That positive indicates to the right. Feel all right? Now we say, okay, well maybe this occurred with some measured amount of time. Let's say that it took some amount of time for it to go from start to end. How long did it take? Well, let's say it took 2 seconds. We introduce this quantity of time. Now we look at all of the quantities we've seen so far. Position. Position is a vector. Displacement. Displacement is a vector. Time, for us, time is a scalar. Time is different than position. Time is different than displacement. Time is a scalar value. That'll be important here in a second. So we have our displacement, our delta S, and our change in time, in other words, our delta T of 2 seconds. And we do for our change in times, time represents by a lowercase t. We have a change in time of 2 seconds. And we can describe our velocity as being our displacement divided by how long it took. What does this mean? This means that if the time is smaller, the velocity is larger, meaning that we undertook the motion more quickly, more rapidly. So if we have a change in displacement over some time, we can describe the velocity as being that change in displacement over time. What is our change in displacement? 10 meters i-hat. What is our change in time here? 2 seconds. And when we start to do this math, right, 10 meters divided by 2 seconds, what we're going to do is split this up into 3 parts. We're going to say there's a numerical part, 10 over 2. Oh my gosh, all my black markers are dying. Okay. So we have 10 over 2. That's the numerical part. And just pop quiz, 10 divided by 2 is? 5. Wonderful. So 10 over 2, that'll give us our 5. Then there's going to be a unit part. We put the units in the next piece. We have a meter on top and a second on the bottom. Meters over second. So we have a numerical part, a unit part. What is the third part? The third part is going to be the vector component. I-hat. So we have 10 over 2 meters per second. I-hat, in other words, our velocity is given 5 meters per second I-hat. And that I-hat tells us something. That I-hat tells us what? Direction. Tells you where you're heading. I-hat means to the right. Positive I-hat means to the right. So this tells you we're heading 5 meters per second to the right. What do we have here? We have a quantity with some magnitude as well as some direction. We have a quantity with magnitude and direction, and whenever we have a quantity that has a magnitude and direction, what do we call that? Vector. Velocity is also a vector. Velocity is a vector. Though you can describe it as our displacement over time. We'll kind of be a little more specific about it in a moment. Do we feel okay about this? Any thoughts, any comments? Okay. So, if it took 2 seconds to go from -6 to 4, where do we think it was after 1 second? If we know that it was at -6 meters when the stopwatch was at 0, and we know it was at 4 meters when the stopwatch was at 2 seconds, my question is, where was our object located when the stopwatch was reading 1 second? -1 meter. How do we figure -1 meter? Well, we figured -1 meter because we are traveling 5 meters every second. We're traveling 5 meters every second. So that means that if we were to look at our position as time progresses, we can say, well, at a time 0, we were at a position of -6 meters. At a time of 1 second, we were at -1 meter. At a time of 2 seconds, we were at 4 meters. At a time of 3 seconds, we are at where? Where do we predict we will be at 3 seconds? 9 meters. Sounds good to me. What about 4 seconds? 14. So we'll write those in. 3 and 4. What about 7 seconds? Where are we going to be at 7 seconds? Figure it out. Tell your neighbor where you think the location will be after 7 seconds. Okay, so where are we after 7 seconds have passed? Raise your hand if you have an answer. 29 meters? Does that sound right? 29 meters. I saw a hand to go get 29 meters as well. 29 meters, sure. We're at 29 meters. How do we know? Well, we don't know for certain, right? The only information I gave was 2 pieces of information, start and end. What did we do from that? We extrapolated a velocity, and we made a prediction about location in the future. This is the power of physics. Power of physics is making predictions based on partial data sets. We have a partial data set, a start and an end, and we make a prediction as where it's going to be. Now, this is a very good prediction so long as your velocity is constant. That's the assumption being made. Any prediction that we have relies on assumptions. Here are assumptions. Is that our velocity is constant. And we'll work on that assumption. We'll say velocity is constant. And what would that look like as time progresses? 1, 2, 3, 4, 5, 6. I'm going to graph out position versus time, the data set that I have on the board over there. And at a time of 0, we are at -6 meters. We agree with that, yes? At a time of 1 second, we should be at -1 meter, somewhere around there. At a time of 2 seconds, we should be at 4 meters, somewhere around there. 3 seconds, we should be at 9. somewhere around that location right there. 4 seconds at 14, somewhere around right there. 5 seconds, we can continue going on. 5 seconds will be at 19. So we'll go ahead and fill that in. And then I don't have any more vertical space, so we'll stop. So we graph out position versus time. Seem okay? Graph out position versus time. And what do we notice? Well, if we make the assumption of constant velocity, our graph ends up being a straight line. Well, as straight as I can make it by hand. But we end up with a straight line for our relationship here, right? And mathematically, we know how to handle straight lines. Mathematically, we say, straight line, my algebra teacher drilled it into me. A straight line can be represented as saying the vertical position is given by the slope of our line multiplied by our horizontal position, x. Remember, this isn't x position. This is our horizontal axis. And then we add to that what? Our y-intercept. Say plus our y-intercept b. Sound all right? All right, well, what do we have here? Our vertical position is going to be, or our vertical coordinate is s, right? Our position. We put position on the y-axis. I'm going to swap out y for s, just to take it from this abstract mathematical thing to this very real physical concept. We say, okay, well, that's s. We have our slope. Our slope is going to be rise over run. So we take this and we say our slope, I'm going to just have m there to represent slope as we would normally do, but this is our slope. And then we have our x-coordinate. Our x-coordinate is time, t. And then what is our y position? Our y-intercept? Our y-intercept is where we go through the vertical axis. And when is that? That's at time t equals 0. Well, that's interesting. That is your initial position. Your y-intercept here, where your line crosses the vertical, that is your initial position. Does it sound okay so far? Any thoughts, comments? We take this and we say, I'm going to rearrange this a little bit. I'm going to say that s minus s initial is equal to slope times time. Sound good? Well, taking a position, subtracting off your initial position, taking your position, subtracting off your initial position, that's what we described as displacement. Yes? So we could say this is your displacement. Delta S is equal to slope times time. Right? Okay, well now let's do a little bit more algebra. Let's divide both sides by time. And what do we get here? We get that slope m is given by displacement over time. But hold on, we have a way to talk about displacement over time. Displacement over time is what physical quantity? Velocity. So the displacement over time is your velocity. What does that mean? That means your slope here is a representation of your velocity. So whenever you have a position versus time graph, we have the slope of your position versus time graph giving you your velocity. Again, though, this is just describing velocity the same way we were doing it before. Describing velocity as being your displacement over time. Describing your velocity as being how quickly does your displacement happen. In other words, what is the slope of your position versus time graph? Well, slope is just a way to say rate of change. This is saying your velocity is the rate of change of your position. So what is the definition of velocity? Definition of velocity is that velocity is given by the rate of change of your position. Velocity is the rate of change of your position. You want to Solid definition for velocity was rate of change of position. So your velocity vector is the rate of change of your position. How might we investigate this a little further? How might we investigate this a tiny bit further? Well, velocity being rate of change of position. In mathematics, when we talk about a rate of change, we're talking about the calculus definition of a derivative. Talking about the calculus definition of derivative. So what is our velocity? Our velocity is defined to be the rate of change of position. In other words, the derivative of position with respect to time. Now, what kind of calculus am I going to be expecting of you in this class? Am I going to ask you to do any tough derivatives? No, I'm not going to ask you to do any tough derivatives. What will the calculus look like in this class? The calculus in this class will look like, here is a graph. Tell me what the velocity is. Well, yeah, it's just finding the slope. Finding the slope is calculus. That's what calculus is there for you to do. Calculus is there for you to find slopes of tangent lines. That's what calculus does for you. It does some other stuff too. But it finds slopes of tangent lines. So perhaps I give you a different motion. Perhaps I say, here's an object that is undergoing some motion, which it starts at 18 meters, and it is going to proceed to undergo motion, which takes it through, I missed that mark a little bit, and takes it through that, and takes it to the origin in 5 seconds. So what does this look like? Well, this looks like some object that starts at 18 meters and goes towards the origin, and let's pretend this is a straight line. What does this look like physically? Well, physically this would look like, here is our number line. Here is our position of, we'll call this 20 meters, 18, 16, and then we're going to go all the way until we eventually reach 0 meters. So what does this look like? This is going to be an object that starts at 18 meters and takes 5 seconds to get to the origin. All right, well, what is the velocity? What is the velocity? Well, calculus says the velocity is going to be the slope of this line. So we find the slope of this line by looking at rise over run. Slope is defined to be rise over run. So we look at the run. In this case, the run is 5 meters. And the 5 seconds, thank you. And the rise, well, the rise is going to be 18 meters, but it's 18 meters downwards. So we say the rise is negative 18 meters, the quote-unquote rise. So then what is the slope? Well, the slope would be negative 18 meters over 5 seconds. Negative 18 meters over 5 seconds. What does this give you? What is negative 18 divided by 5? What is it? Someone raise your hand. Someone who's confident in their answer. I think I heard the right answer over there.
Negative 3.6 meters.
Negative 3.6 meters. Is that what I heard over here as well? Someone said it. Seems nods. Negative 3.6 meters per second. Negative 3.6 meters per second. What does that mean? That means that the velocity is negative 3.6 meters. We determined that using calculus. Using the power of calculus, we determined the velocity is negative 3.6 meters per second. The negative tells us what? The negative tells us to the left. And that confirms what our theory is, that our velocity should be to the left. So we have Negative 3.6 meters, that means we are moving 3.6 meters every second. We are moving 3.6 meters to the left every second. All right, any questions about this? Any thoughts, comments? All right, so then you proceed to say, but Professor Martinez, this is far too easy. This is far too easy, dealing with one dimension. I can handle multiple dimensions. What changes when we have multiple dimensions? Well, not much changes. Not much changes. Because when we have multiple dimensions, we look at our velocity and we say our velocity is dependent on some position change, some change in position. So we might define some initial position to more generally be written out as some location horizontally. I'm going to use x here to represent how far left and right this object is. X I hat plus y j hat. And if you wanted to put a z component in there, you can put a z component in there. But x is just a stand-in for some number. Maybe x is 3, meaning that we're 3 meters to the right. Maybe it's negative 2, meaning 2 meters to the left. You might have this representing your initials, and you might have some final position represented by x final I hat plus y final j hat. Again, x final and y final, x with the subscript f and y with the subscript f, just stands in for some number. So we have these initial and final locations. Sound good? We then go on to say, well, generally speaking, we can write out a displacement, delta s, as being, we've done this a couple of times, the difference in our x components multiplied by I hats, added to the difference in our y components, y final minus y initial, in the j hat direction. So we find our displacement, and this is again just more generally where x final and y final, they stand in for just something. We then move on to say, well, what is our velocity going to be? Our velocity, yes, it is defined to be the derivative of our position with respect to time. But if it is the case that the velocity is unchanging, meaning it's not speeding up, it's not slowing down, it's not changing direction. Remember, velocity is a vector, meaning it has a magnitude and direction. So if your velocity is maintaining its magnitude and its direction at some constant value, it's not changing. It's going in the same speed, same direction for as long as it's moving. But if this is true, then what we have is that the velocity is just given by displacement over change in time. Simplifying things a little bit to the point where we can say that your velocity is then equal to your displacement, x final minus x initial, I hat, plus y final minus y initial, j hat, and divide that by the amount of time that has passed between initial and final. Now, this is kind of an inconvenient way to write it from the fraction point of view. So instead, we might take a different path. We might take a different path in which we break up the fraction. We break up the fraction a little bit to give us some velocity vector as represented by x final minus x initial over time in the I hat direction plus y final minus y initial over time in the vertical direction. And then if you wanted to expand this out to 3 dimensions, what do? Well, z final minus z initial over delta t. And we use k hat to represent our third dimension. Now, again, in this class, we're going to be sticking mostly to the first two dimensions, vertical and horizontal. Not until much later will we see a dimension in that third direction. And when we do, we're not going to be doing this exact stuff. But this is how it would play, and you would just add it in as third piece. And this gives you a definition for your velocity. And this is the more broad definitions. What do we say? We say, to describe motion, I define some position. If that position changes, I can have a displacement. And from that displacement, I can analyze how quickly that displacement happens, what the rate of change of that displacement is. But this is all assuming constant velocity. What happens if we are speeding up? What happens if we're slowing down? What happens if we are turning? Under the cases where we are speeding up, slowing down, or turning, we then talk about a physical quantity of acceleration. Acceleration describes something that changes in velocity. And that's what we will be doing next. Before you guys head out, we have a couple more minutes. Before you guys head out, first I want to ask, are there any questions, any thoughts, any comments, or any concerns? Feel good about this? You'll get a lot of practice with it. Your second homework assignment, I believe, is already out. Your second homework assignment is already out, and that does have stuff related to this motion stuff that we're working on. Alright, so what I'm going to do now is I'm going to hand out for you all these little slips of paper, and these little slips of paper have a bunch of equations on them. You might wonder, Professor Martinez, why are you handing out these little slips of paper? I mentioned earlier that we're going to have exams in this class. I mentioned that at the start of the semester. We're going to have exams in this class, and I'm not expecting you all to memorize every single equation. So what we're going to have is these sorts of little cheat sheets. These little slips of paper will serve as your cheat sheets on the exam, and throughout the semester you will get different little slips of paper with different equations on them. This is what you will be allowed in the exam. Now the first one I handed out has a bunch of vector stuff on it. I color-coded vectors to be pink. Why did I do that? Well, I asked someone in lab today what color represents vectors, and they said pink. The second slip of paper has a bunch of kinematic stuff on it. Kinematic is the study of motion. Kinematics is the study of motion. And our study of motion begins with this position, displacement, velocity, and acceleration. So that's what's on this green paper, is definitions of these different quantities. Now, are you going to get every single equation in this class now? I'm going to give you the basics, what you need. At bare minimum, your responsibility is going to be to understand how to get answers from these bare minimums. There you go. Well, all right. Do we all have these slips of paper? Okay, what I want you to do is attach these to those rings that I passed out earlier so we can all keep them together. You're going to attach these to the rings, and again, these are what you're allowed to bring into the test. You'll get a bunch of these throughout the semester. Any questions, thoughts, comments, concerns? All right, now, next thing I want you to do, on the first one, on the vectors one, I want you to write your first and last name on the top right of that one. That way I could identify whose is whose. I will be checking them during the exam to make sure that you guys didn't write any excess notes on them, because I do want these to be what you have, nothing more, nothing less. Yes. All right. There you go. All right. So I think that pretty much wraps up what we're going to do today. Last second questions, comments, concerns? All right. If you guys have anything or if you want to stay for office hours, I am going to be doing office hours in this room directly after you guys leave. So if you have any questions, just stick around and I'll be happy to answer them. A few people needed to add the course. If you needed to add the course, please come up and talk to me post-haste. Otherwise, have a wonderful rest.